Welcome back to the deep dive. We're here to really cut through the noise on the topics that count. And today, we are definitely plunging into one of those topics. It's exciting, sure, but also raises, whoa, some pretty serious questions for a lot of people. Large language models, LLMs, we're all, kind of amazed by what they can do. But there's this growing conversation, right? And even legal challenges like that big New York Times lawsuit against OpenAI, really questioning how these things handle all the information they learn from. Okay, so let's try and unpack this a bit. A really central question seems to be whether LLMs actually store copies of the data they're trained on, especially personal stuff. If you've ever wondered what's actually going on inside these pretty complex models when they learn from, well, basically the internet, then this deep dive is definitely for you. Our vision today, let's demystify how LLMs process and handle information. We'll look at their core parts, walk through the key stages like tokenization and embedding. Then we'll compare how they handle data versus, normal storage systems.
We'll try to get our heads around memorization and, crucially, look at practical ways to manage the risks with personal data when using LLMs. So let's start right at the foundation. When we talk about an LLM, what is it physically? It's not like a giant hard drive packed with web pages, is it?
No, not really. Fundamentally, an LLM is software. It's mainly defined by, say, three core components: a parameter file, a runtime script, and configuration files. The runtime script, that's the code, the algorithms telling it how to run, but the parameter file, that's where most of the magic, the intelligence, actually lives.
Okay, and these parameters, they aren't the raw data itself, are they? You hear weights and biases. These are the numerical values that kind of guide its predictions. Can you break down what these parameters really are and why having billions or even trillions of them is so important?
Absolutely. Yeah, think of parameters as countless tiny adjustment knobs inside the neural network. Billions, trillions sometimes. Each knob, a weight or a bias, sets the strength of a connection between different points, different nodes in this network. During training, these knobs are constantly being tweaked, fine-tuned. The final numbers they land on after seeing, petabytes of data are the model's learned knowledge. They encode all the patterns, the relationships, the structure of language it's picked up, and the sheer number of them lets it capture incredibly subtle, complex connections in the data. That's why they seem so good at understanding and generating text that feels human. So together, yeah, these components form a neural network. It's more like a dynamic brain than a static file cabinet.
A dynamic brain, I like that. Built on these super complex, interconnected parameters. Okay, so how does this network actually take in and learn from that massive amount of data? Which brings us to that first step you mentioned, tokenization.
Exactly. Tokenization is step one. All that raw text data gets broken down into smaller units. We call them tokens. Now, you might first think tokens are just words, and sometimes they are, but usually LLMs use something more efficient called subword tokenization.
Subword tokenization.
Oh.
Okay, so not just whole words, but parts of words like prefixes and suffixes.
Yeah.
That sounds like it would give it more flexibility. Can you give an example?
Sure. Take a long word, like pseudonymization. Instead of one token, it might break it into pseudonym and ization, or maybe reacting becomes react and ing. Each of these becomes a token.
Okay, and the benefit.
Not several big ones.
Right, and here's where it gets really interesting, isn't it? Because it's not just splitting words, it's like giving the LLM a more fundamental alphabet. Does that mean it ends up with a much smaller vocabulary overall? Because things like re or ink get reused all over the place.
That's exactly it. A smaller, more adaptable vocabulary. Makes training faster, makes using the model faster too. Plus, it helps the LLM handle words it's never seen before, OOV, or out-of-vocabulary words. If it sees a new word, it can often break it down into known subwords and still make some sense of it. And crucially, each token word or subword gets a unique number, an ID. That mapping, token to ID, is stored in the LLM's vocabulary, which is part of its configuration. That vocabulary is essential for, turning input text into numbers the model understands and turning the model's numerical output back into text.
Okay, that makes sense. A really efficient way to digitize language.
Yeah.
So you've got these numerical tokens. How does the LLM start to pull out meaning or context? This must be where embedding comes in, right? That second stage.
Yes, embedding is where the context happens. It's a mathematical process, really. The LLM learns to represent the typical context of each token based on how it was used in all that training data. And this context gets encoded into a list of numbers, a vector. Every token gets its own vector.
Okay, vectors. I sometimes try to picture these as like unique numerical fingerprints for each token. Is that a decent way to think about it? Where similar fingerprints mean similar meanings.
That's a great analogy, actually, yes. The closer two token vectors are in this high-dimensional mathematical space, the more similar their meanings or uses tend to be. During training, these vectors get refined constantly. The model learns not just the token itself, but where it usually shows up, what other tokens it tends to be near. And once training is done, these refined token vectors are stored in what's called an embedding matrix inside that big parameter file.
But it's not just the token vectors, is it? You mentioned the network itself, the layers adjusting their weights and biases. How do those contribute to capturing context?
Right, good point. The connections between the nodes in the network's layers also learn context. Think of the weights as controlling how much influence one node has on the next. Biases are like a threshold a node needs to cross before it activates or fires. As the model sees more data, it adjusts these weights and biases. It learns the subtle rules of grammar, the common ways words combine, the semantic relationships. So the network structure itself, through these learned weights and biases, embeds a deeper layer of contextual understanding as information flows through.
And the result of all this complex math,
Yeah.
how does it let the LLM actually write something coherent?
Well, at the end of the day, all these embeddings, the token vectors, the learned weights and biases, they all work together to influence the probability of which token should come next. That's fundamentally how LLMs generate text. They predict the most probable next token, then the next, and so on, based on the sequence so far and all the patterns they've learned. And what's really quite amazing is the subtlety here. The LLM learns that after, say, the token tokens like mind or turn are very likely because remind and return are common words. But maybe purpose is less likely, unless it saw a lot of technical text where repurpose is common. And something like step to make restep would be incredibly unlikely because it's just not standard English. It's all about these probabilities learned from massive amounts of text data.
That's a great illustration. It really shows it's about probabilities and patterns, not just rote memorization. Which brings us right back to that big question, the one causing so much debate. Do LLMs actually store personal data like, say, a spreadsheet or a database does?
Yeah, the core question, and the straightforward answer is no. Not in the way we normally think of data storage. Think about traditional systems, databases, spreadsheets, even document folders. They're built to keep information intact, often linked directly to a person. And they're designed for specific queries, for precise retrieval. You ask for customer X's billing address, you get exactly that record. The link is preserved.
Right, so how is the LLM approach completely different, especially with personal info?
It's fundamentally different by design. LLMs, as we've seen, don't store data that way. During tokenization, any personal data in the training set gets chopped up into subwords, right? It's processed, changed from its original form, and the vocabulary, it stores the tokens and their IDs, yes, but it crucially does not store the connections, the associations between different data points that would link them back to one specific person.
Okay, so going back to an example you mentioned before, if Coleman Wong, the tennis player, and Coleman Street both appear in the data, the LLM just ends up with a token for Coleman. It doesn't inherently know one is a person and one is a place.
Exactly right. The vocabulary just has the token Coleman. Now, the model's embeddings might learn that Coleman often appears near words like tennis or Singapore or maybe near street or avenue. It learns these general patterns of association. But it's not storing a specific database record for Coleman Wong with his address or for Coleman Street with its location. It generalizes from the patterns. It doesn't retrieve specific entries. It learns how names and addresses are typically structured, connecting this to the bigger picture. The whole process, tokenization, embedding, it fundamentally changes the data's nature. It's not built to remember who lives where. It's built to understand linguistic patterns. This structure is also why LLMs can sometimes hallucinate, generate plausible but wrong information. They're following learned patterns of what sounds right, not recalling stored facts.
That's a really, really crucial difference for people to understand. So the key point is the data inside an LLM, the tokens, the embeddings, essentially loses the quality of being personal data because those identifying links just aren't maintained. They're not designed for that kind of lookup. Huge privacy implications there. But okay, if they don't store data like that, what about memorization? We hear about LLMs sometimes spitting back specific phrases or sentences they saw during training. How does that happen?
Right, memorization, or sometimes called partial regurgitation. It's not retrieval from storage, it's more like an echo. It happens when a specific sequence of words or phrases appeared a lot in the training data or very consistently in a certain context. If a pattern is seen over and over again, the model learns an extremely high probability for predicting that exact sequence. Think of it like learning a song lyric so well you just automatically complete it if someone starts singing the first few words. It's probabilistic recall, not database lookup.
And I guess this is related to standard machine learning issues like bias and overfitting.
Absolutely, spot on. Bias in the training data is a big factor. If certain phrases or facts are massively overrepresented, the model becomes biased towards reproducing them. And then there's overfitting. That's when the model learns the training data too well, including noise and specific examples instead of just the general patterns. Both of these make memorization much more likely, especially for things like famous quotes, common code snippets, or yes, personal information if it appeared frequently enough.
So let's take that Lee Kuan Yew example again. Singapore's first prime minister, 38 Oxley Road. That specific name and address combination likely appeared many, many times in news articles, historical documents, etc., in the training data.
Exactly. So the model learned a very high probability for the token U following Lee Kuan, and for 38 Oxley Road appearing in the context of his name. It can reproduce that string because the statistical likelihood is overwhelming based on the data it saw. But again, it's crucial to remember, this is reproduction, driven by probability. It's not retrieval of a stored record about him. And often, this reproduction isn't perfect. It might be paraphrased, maybe slightly wrong, incomplete, maybe it gets the job title slightly off. Because it's generating based on patterns, not pulling a file.
That makes sense, and it connects to those stories where an LLM just confidently makes something up, a hallucination. That's also this probabilistic generation at work, right? So creating what seems statistically likely even if it's totally false. So this brings up a critical point.
Yeah.
If it's probabilistic reproduction, not retrieval, what does that mean for privacy? Reproducing famous public details might be one thing, but for a private individual, that feels very different.
Completely different. Those hallucinations.
Yeah.
Yes, exactly a result of probabilistic generation. It predicts the most likely sequence, even if that sequence doesn't match reality. And you're right, the implications for private individuals are serious. While reproducing publicly known facts about a famous person might be, well, expected, the same is absolutely not true for private citizens. The risk is that if someone's personal data appeared frequently enough in the training data, it could potentially be reproduced through this probabilistic mechanism, even though it's not stored in a directly accessible way.
Okay, so the picture is, LLMs don't store or retrieve personal data in the traditional sense, but they can sometimes reproduce it due to patterns in the training data. So the focus has to be on safeguards, right? What can be done, both in building these models and when using them.
Precisely. Since the design isn't for storage, but reproduction is possible, mitigation is key. During model development for the people actually building the LLMs, the best practice is, frankly, to avoid training on personal data altogether if possible. If it is unavoidable, then you apply techniques to the training data itself. Things like pseudonymization, replacing names with placeholders, data minimization, just stripping out personal data that isn't needed, and techniques like differential privacy.
Differential privacy, that's adding statistical noise, right, to sort of obscure individual data points.
Exactly. It adds carefully calibrated noise so that the overall patterns can still be learned, but individual data points are protected. Mathematically provable privacy. And even after training, there's research into things like machine unlearning, trying to selectively make the model forget the influence of specific data without having to retrain the whole massive thing.
That sounds complex but important. Okay, so that's on the development side. What about for organizations or individuals using these LLMs? What practical steps can we take right now? And I suspect this is where that concept of grounding comes in. You're saying the LLM is great for fluency, for making things sound good, but we need to give it the actual facts, especially if personal data is involved.
Yes, grounding is absolutely critical. It's about providing the LLM with trusted external information to base its response on. So practically, if you're using an LLM for a task, first see if you can remove personal data from the trusted sources you're going to feed it. If you need personal data for the output, then you should store that data securely in your own systems, your database, your knowledge base, and retrieve it using traditional secure methods. Then you feed that specific verified data to the LLM as part of the prompt.
Okay, give us an example. How would that work in, say, a real-world scenario?
Sure. Let's say you want an LLM to help draft an updated CV for an employee. You wouldn't just ask it, write a CV for Jane Doe. Its internal knowledge might be wrong or outdated. Instead, you'd ground it. You'd give it Jane's old CV, maybe a link to her current internal profile page, and the job description she's applying for. You provide the reliable source material in the prompt. The LLM then uses those specific documents you provided, documents you control and trust, to generate the new CV. It's relying on your input, not its vast, potentially inaccurate, pre-trained knowledge base.
Got it. So you're controlling the factual inputs. And isn't there a more automated way of doing this, retrieval augmented generation or RAG. How does that fit in?
Yeah, RAG basically systematizes and scales up that grounding process. It's very powerful. The basic idea is a user asks a question. The system turns that question into a vector. It then searches a special database, a vector database, that contains embeddings of your own trusted documents, maybe your company's internal wiki, product docs, whatever. It finds the document sections most relevant to the user's query based on semantic similarity. Then, it automatically takes those relevant snippets and adds them to the prompt that goes to the LLM. So the LLM gets the user's question plus the relevant context from your trusted data all in one go. It dramatically improves accuracy and reduces reliance on the LLM's internal, potentially problematic knowledge.
That's essentially giving the LLM an open book test using only your approved books.
Yeah.
Makes a lot of sense. What about stopping sensitive data getting in or leaking out accidentally during use? Are there filters?
Yes, absolutely. Data loss prevention, or DLP, is crucial here. You typically implement filters on both sides. Prompt filtering tries to catch and block sensitive information, like maybe credit card numbers or social security numbers that users might accidentally put into their prompts. And output filtering scans the LLM's generated response to try and catch any accidental reproduction of sensitive data before it reaches the user. They act like safety nets.
Okay, so we have grounding, RA, filtering. But even with all of that, we still need to remember the LLM is fundamentally probabilistic, right? It's not infallible.
Absolutely, that's the bottom line. Even with perfect grounding, the LLM is still generating text based on probabilities. It can still misinterpret the provided context. It can paraphrase poorly. It can combine facts incorrectly. It can still hallucinate to some degree, which is why, no matter how good your grounding or filtering is, human oversight vetting and correcting the output remains absolutely essential, especially for anything important or sensitive. You just can't skip that final check.
A really critical reminder. Human judgment is still key.
Wow, this has been incredibly clarifying. So just to quickly recap, we've established LLMs don't store data like databases. They learn incredibly complex patterns from language, represented by tokens and embeddings. That memorization we sometimes see, it's not retrieval. It's probabilistic reproduction of very common patterns. And managing the risks, especially around personal data, is a layered approach. Careful model development, yes, but crucially for users, strategies like grounding the LLM with trusted external data using techniques like RAG and robust filtering, plus that essential human review. So next time you interact with an LLM, maybe remember it's less like a library and more like a super sophisticated pattern matching engine, predicting what comes next. Understanding that difference really helps us use its power safely, which makes you think, how will this fundamental distinction shape the way we design our future interactions with AI? How do we harness the fluency but ensure the facts and safety? Something to ponder.